Welcome, and thank you for joining us today. In this presentation, we will guide you through our IoT data analysis and security project. Our work combines data processing, machine learning, deep learning, and secure communication techniques to classify daily activity levels using data from wearable devices. Throughout this session, we'll show you how each component comes together to create a dependable and secure smart health solution.
Our system is built from real Apple Health data collected from three anonymized users. We built a complete pipeline that goes from XML extraction to cleaning to daily feature generation, and finally into two branches of analysis: non cryptographic ML models and cryptographic and secure ML models. Data collection. We exported raw Apple Health XML files, which include readings from sensors like accelerometer, the gyroscope, GPS, and motion trackers. Using our extraction script, we kept only two privacy maintaining metrics: the step count and walking running distance. We converted each user's XML file into a CSV and managed the data securely using Git LFS. The data processing pipeline. We processed everything locally to protect sensitive information. Our processing script merged all three users, aggregated the data into three final features: steps total, distance total, and a calculated activity level label: low, medium, high. This created our final data set, which was called the Combined Daily CSV.
For this project, we evaluated our models using three complementary strategies. First, we applied 75-25 random split, which served as our baseline performance check. Next, we used group by user split to test how well each model generalized to completely unseen users, an essential requirement for real-world IoT application. Finally, we performed a time-based split, allowing us to examine how stable and consistent models remained when predicting across different time periods. To assess performance across these scenarios, we use a comprehensive set of metrics, including accuracy, F1 macro, F1 weighted, Matthews correlation, coefficient or MCC, log loss, Breyer score, and ROC and AUC. Together, these metrics provided a balanced view of not only correctness, but also calibration, robustness, and reliability.
For the non cryptographic branch, I developed the machine learning models. We use logistic regression as the main classifier because it's lightweight, interpretable, and works well with simple IoT features. The model was trained using a 75-25 split and standardized with standard scalar. Logistic regression performed well, our accuracy was high, and the confusion matrix shows minimal misclassification across low, medium, and high activity levels. The per class metrics also show strong precision, recall, and F1 scores, which means the model handles each user's behavior consistently.
The second model is an SVM with an RBF kernel, which allows it to capture nonlinear patterns. We use two calibration methods: flat calibration, isotonic calibration. These improve probability reliability, importance if the model is used in a safely critical system. The calibrated SVM generalizes better than the logistic regression and produces more dependable probability outputs.
The XGBoost gradient. The key idea here was to use sequential trees, which improved each other's errors. And it's excellent for tabular IoT data. The findings that we had for this model was that it performed best in splits, and the feature importance, the total steps total and distance kilometers.
In addition to traditional ML, we implemented three deep learning models: a deep neural network, a long short-term memory model, a 1D convolutional neural network. The LSTM and CNN models use 7-day sequences, allowing them to capture weekly behavioral patterns. The DNN captures nonlinear boundaries but doesn't consider time. Its performance is moderate, better than logistic regression, but not as strong as XGBoost. A 1D convolutional neural network extracts local patterns in the 7-day sequence, for example, sudden changes in activity. It performs similarly to the LSTM but trains faster and is less computationally heavy. The LSTM is designed for sequential data. It requires daily patterns over the 7-day window. The model performs well at capturing trends, but the dataset is relatively small for deep learning.
To summarize our findings, XGBoost delivered the highest overall accuracy and proved to be the most effective model in general. And calibrated SVM provided the most reliable probability estimates, making it strong for decision-making scenarios. And LSTM and CNN models demonstrated solid performances in capturing time series patterns, which is valuable for sequential activity data. And logistic regression served as a lightweight baseline offering fast computation and easy interpretability. Overall, XGBoost and calibrated SVM show the strongest performances when tested on unseen users and time-based data splits, indicating good generalization.
Activity data is highly sensitive. Ethical risks include loss of privacy, secondary misuse, lack of transparency, algorithmic bias, overcollection of unnecessary data. Mitigations we used minimal additional metadata, local only processing, no GPS or timestamps, encryption for transmissions. At a state level, health IoT data can reveal population movement patterns, mass surveillance potential, automated governmental decision making risks, misuse of analytics on a societal scale. This emphasizes the need for secure, transparent, and regulated data handling. IoT health systems offer major benefits real time insights, behavioral monitoring, improved medical decision support, emergency response enhancements, large scale health analytics. However, IoT devices also introduce risks data interception, device spoofing, metadata leakage, firmware exploitation, replay attacks, man in the middle attacks. We addressed these risks through modern cryptographic protections. To secure IoT transmissions, we implemented three modern cryptographic methods authenticated encryption with associated data, encrypts the data, and verifies integrity, and binds metadata, like device ID, through AAD, prevents tampering, and ensures messages cannot be forged. Hybrid public key encryption. It securely exchanges encryption keys between devices. It provides forward secrecy, protection against interception, strong confidentiality even over insecure networks. This ensures only authorized devices can decrypt data. Object, object security for constrained IoT devices. Oscar is designed specifically for IoT sensors. It adds replay protection using partial 4, nonsense to prevent message reuse, key rotation for long term security, end-to-end integrity protection. Together, these mechanisms protect sensor messages even if intermediate networks are compromised.
In our real life example, we looked at the aviation industry, which relies heavily on IoT systems for both operations and safety. Airlines collect extremely sensitive data, including crew biometrics, such as fatigue levels, passenger flow, and movement patterns, predictive maintenance telemetry from aircraft components, and even passenger biometrics used for automated boarding systems. There is also information that must never be leaked, for example, pilot fatigue predictions or the internal health of aircraft components. These datasets can reveal operational weaknesses or safety critical details. If this data is compromised, the impact is severe. Attackers could manipulate predictive maintenance information and create safety risks that track the movements of crew or high profile passengers or cause major operational disruption. There are also strong privacy implications, such as violations of GDPR when biometric data is exposed. Because aviation is classified as critical infrastructure, any breach also has national security consequences. This example demonstrates why IoT systems in high-risk industries require strong end-to-end security and why protecting sensitive behavioral and biometric data is essential for both safety and trust.
In closing, our results highlight how each component of the system contributes to a stronger and more secure IoT analytics pipeline. XGBoost proved to be the most effective overall model, while the calibrated SPM provided the most dependable probability estimate. The LSTM and CNN models also showed promising potential for future time series expansion. Overall, this project demonstrates how machine learning, deep learning, and IoT security can work seamlessly together to create a reliable, privacy aware activity classification solution. Looking ahead, there is still room to grow, expanding the dataset with more users and richer features. Implementing drift detection with automated retraining and exploring transformer based deep learning models will help elevate performances even further. And by maintaining a full AEAD, HPKE, and Oscar secure pipeline, we can ensure that the system remains robust and protected end to end. And that would be it for our presentation. Thank you for listening, and we hope that you enjoyed.